So my presentation's on CAPI, which is a Coherent Accelerator Processor Interface, a new innovation that we've put on the Power 8 servers from IBM. 3 parts to the discussion. I'd like to try to make it interactive. I know that I've got 35 minutes or so before we start up the panel and maybe change things up. So questions during my talk are welcome. 3 parts to the discussion. First is just why we came about doing something like CAPI and also our GPU interface. The second is what is CAPI, just a little bit of an overview, and then the third are some demos of usage cases with CAPI. So to end where we began, Steve first talked about Moore's Law this morning. So I threw a chart in here, more complex than what probably has to be, but it's talking about Moore's Law. And this is why we ended up building the Power 8 server the way that we did. This is the trajectory that Moore's Law is supposed to be on, but in the last bunch of years, this red line is Intel's trajectory. Now, it's a little bit different on the vertical graph. It's price performance, not just performance. So what was happening is that Intel, while it was getting harder to scale, they were not dropping the price the way that the price had always been dropping. And this led people to be worried, including companies like Google, who were relying wholeheartedly on x86 processors. And if x86 jacked their price up, what could Google do? That helped drive them to make some moves that they've recently made. But as we watch this trend around 2010, which is the point in time in which IBM was starting to think about the Power 8 servers, which came out in 2014, we realized that you can no longer rely on the scaling alone, and that to deliver the performance, the system-wide performance that we need, you have to innovate across all levels of the platform, not just semiconductor technology and processors, but firmware, operating system acceleration, all the way up to the applications and services, growing out, using FPGAs, using GPUs, and not just relying internally on IBM being a closed box, but open up the system. And this led us, along with companies like Google, Mellanox, NVIDIA, to create an organization called Open Power. Today, Open Power has over 180 members. You see here Xilinx, NVIDIA. Of course, IBM is in here, Google's in here, and a couple different places. The membership includes research, everything from software, middleware, all the way down to chip. And this is important because the products that we're seeing are no longer just, here's an IBM product with IBM software. But the very first CAPI product we put out was the IBM Data Engine for NoSQL, which was a Redis software with Ubuntu operating system built on a Nalatech card with, sorry, but it was Altera technology. And of course, an IBM server. So 5 different companies coming together to make a product that was really quite relevant to the NoSQL world. So that's the landscape that we came into as we started to create what we see as the most powerful heterogeneous compute platform there is. We have NVIDIA for GPU, and we have this CAPI for FPGAs. So the rest of the discussion will go into some of the things that we're doing on CAPI. So Coherent Accelerator Processor Interface. What's new about that? Well, accelerators have been around for a long time. What makes this different is coherency out on the FPGA. And fundamentally, what we're doing is making the FPGA look like it's just another thread on the processor, removing a whole lot of overhead, removing the device drivers, and making it much easier to program. So I'm going to show 2 charts here about what was done before CAPI. This happens to be a Power 8 server mock-up. Power 8 server, each chip has 6 cores, a very large memory, It also has a few other I/O devices and a CAP unit, which I don't show here, but I'll show in a minute. Every module that we put down in a Power 8 server actually has 2 of these chips on it in our scale-out servers. So 12 cores per socket. So what we have here is an application that wants to go and use the FPGA. This is before CAPI, what was done. So the first thing the application does is set up variables and input data and put it in, and it stores it in what it thinks is memory, maybe its own address 1000, but it's someplace in virtual memory that's handled by the subsystem. The next thing, the application has to then call device driver. The device driver takes over, and a standard device driver is going to go and make a copy into its own storage area of the data and the variables. And then the device driver itself owns the FPGA and taps the FPGA and says, go, take the data out of the device driver, bring it over, start your computation. Now, there are many companies that we've come into who have recognized that this is a significant overhead and trim their device drivers down. They do things like zero copy or pinning their data, so they didn't actually have to do the copy, but they lock this data out by saying the application no longer owns it, the device driver does. So there's all kinds of tricks to try to bring this down, but in the end, you no longer have coherent data between the 2 of these. Now, when the FPGA is done, it stores the output data back out and then puts it into the virtual address space where finally the application can see the results of the work. That is today's standard for how an FPGA works through a PCIe interface. Questions on that? Make sense? All right, so far so good. So now, 3 versions of the data, not coherent, and thousands of device driver instructions. Here's CAPI. Looks almost the same with the exception of I added the power service layer, which I'll talk about in a minute, to the FPGA. So it's going to take up a little bit of real estate on the FPGA. Application still has to set up the variables and the input data, but there's no device driver call. Instead, the application itself reaches out, tells the PSL, I've got another thread of work for you to do. The FPGA now has a thread of work to do, and because the memory, this is pink in here, just like the memory, and just like here, because this is all shared memory, the FPGA just gets part of that virtual address space and access to the data. The application during this time that the FPGA is working can still look at that virtual address space. There's no locking it out. And the data, when it's done, gets stored back into the virtual address space. Steve?
On the power service layer, is that still running effectively over PCIe?
Yes. So the transport here is still PCIe. If I go back, I think, it says it there. So the electronics are PCIe, the electricals are PCIe, right? Which still incurs a latency of about 300 nanoseconds to do that, just to get across the bus, all right? But the removal of the device driver and all of the overhead having to do with that actually cuts the latency in half. And we've got some data that shows that. Okay, any other questions? So this is, at a high level, the difference between standard PCIe, FPGA, and CAPI. So so now let's take a deeper look. This is an actual chip picture of the Power 8 processor. It's 3 cores down here, 3 cores here, and a whole lot of memory in the middle. And of course, there's interfaces to go off to DIMMs on the side. This happens to be an Alpha Data Xilinx-based card. Alpha Data is a Open Power partner. They make this PCIe-based card. We actually have 3 or 4 developer kits that all work with CAPI. The first thing I'm going to show is the hardware that we added to the system to enable CAPI. So you have your Power 8 core and coherent memory. And the reason that the memory expands beyond the boundaries of the chip right there is because you've got a second socket or a second chip on the socket and other sockets, and there's coherency across all the cores on all of those sockets. Now here is the coherent application, coherent accelerator processor proxy, or CAP unit. The CAP unit's job is to know what coherent data is up on the FPGA at any given time, so that if another processor, either on this chip or another chip, wants to access the latest copy of the data, the CAP unit will respond on behalf of the FPGA at 3 gigahertz cycle time, really fast, so that we can maintain coherence. So if this core wants data and the latest copy of the data is up in the PSL, then the CAP unit will respond and say, I will get you the latest version and bring it back down this way. So that's the innovation on the silicon that runs at 3 gigahertz that allows you to maintain coherent data up on an FPGA. We had then the PCIe interface and then this PSL that I mentioned, power service layer. Yes? So there are 8 PCI Expresses on a scale-out server with 2 sockets. The question was, how many PCIe lanes are there? All right. So there's 8 different PCIe sockets, 4 of which can be CAPI. So you can have 4 CAPI cards in each 2-socket server. Okay. This one it uses a by 8 width here. We do have by 16s for other work. So the PSL has 3 jobs. First job is caching. There's a 256K cache on the PSL, so that this is, instead of local memory down here, this guy has a local memory up here on the FPGA. When Fernando was talking today about the 9-pixel work and the fact that it had to keep getting data from memory down here, well, now that memory is sitting right there on the FPGA. The second job of the PSL is to do address translation. In the previous slide, I had virtual addressing. Well, the program that's running down here and the application that you've loaded on your FPGA need to talk in the same translation level, so that address 1000 to the processor is the same as address 1000 to here, and the PSL takes care of address translation, virtual to real address translation. The third job of the PSL is to protect the system, so that if you tried to, for example, access memory that is not in your, that you're not allowed to access, it will reject it for you. So it provides a membrane that prevents the accelerator from taking down the system or doing something bad to the system. So those are the 3 jobs: translation, caching, and system protection. And that's what this PSL does. The next thing that we had to do was put the OS to work. And we, first with Ubuntu, but now Red Hat, our own AIX, these distros now have the kernel extensions called libcxl, or library for CAPI accelerator library. This allows the application, through a very simple API, to reach out and do all the functions it needs to talk to the FPGA. So you just do your include, hashtag include libcxl, and that allows you to use the 5 or 6 different library commands in there. And then finally, you have the customer application running on the core that wants to use the accelerator, or accelerator function unit as we call it, up on the FPGA. So you load your logic up here, and your application then can simply call it by putting data in the memory, reaching out, touching the AFU, and then the AFU has access to all of the coherent memory it needs, and it can read and write that data right back into memory. So that's the basic paradigm. We've got all kinds of education, et cetera, that goes into how to use it once we need a deeper level of that. So that's the technology overview there. Questions on that? Yeah.
Oh, does the so the AFU? I'm just looking at the FPGA up there with the IBM supplied. Is that the PSL?
Yep.
So are those can be independently programmed? Is that right?
So you reference being partial reconfiguration.
Yeah.
So we don't use it today,
Okay.
but it was built to do that because as these chips get bigger, there'll be a desire to put more than one AFU on the chip at a time. So if you have, and today it's designed to allow up to 4. So if you want to take one of them down and put a different one up there while another one's running, you should be able to do that. But today there's a one-to-one correlation between the AFU and the PSL, and we just upload it all together.
So in the future, there's going to be some sort of like security mechanism too, right? To keep them.
There already is a security
There is
mechanism.
okay.
Yeah.
Right.
Yeah. So as we boot this, there's a security mechanism with reading the PCIe, and actually when you do an LSPCR from the console, this does not show up as a PCIe card. It shows up as a specialized CAPI card, and it knows that because of the PSL. Okay. So stylized version of it. So you have actually a Power 8 processor has up to 8 threads on it. I'm showing 4 threads running here, memory, and then the attached FPGA. You got your virtual addressing, and this is, and you set up your data. This is just one way of using coherent memory. Just simply the controls become much easier. So a thread goes and he sets up work, puts it in the virtual address space, maybe has another piece of work after that, and now the FPGA can be reading from the head of the queue because it's all coherent and managed by the hardware. The FPGA's read the head of the queue while the thread continues to add more data to the tail. The FPGA can update the head pointer, pulling some of the data it needs down to the FPGA, writing the results back to the virtual address space where this thread can use it. So just like you had 2 different threads that were working on the same data, the only difference is that this is a complete customized core that does exactly what you want. Yeah.
So the memory hierarchy. So in the PSL you have your basically it's an L1 type cache.
Exactly. Yes.
So in order to not have significant delays back to the coherent memory on the chip, how is that managed?
Great question. Yeah. So yeah, it all depends on what architecture you're coming from. So Paul is my lawyer, and in Power, the L1 is always a write-through cache, so that's why he's saying L2. So the FPGA has a context. So if you're writing a VHDL in Verilog, you have a context about what you want to do with that data. If I'm only going to read it once and never use it again, I'm not going to cache it. But if I'm reading it and I know that I'm going to start writing data and reading it again, and then I'm going to want to cache it. And the interface allows you to make decisions like that and choose whether I cache it. If I'm doing a write, I can write it to my local cache, or I can push it back to the system where I know the application wants it. So you have those choices. It's a very broad interface. By the way, IBM does not own this interface. We came up with it, but the Open Power Foundation, and specifically the Accelerator Work Group of the Open Power Foundation, owns this specification of that interface now, so that we can't go and unilaterally change it. We've got a whole set of people who would have to approve any changes to that. And what that does is mean that when you go from Power 8 to Power 9, your Power 8 AFUs will work in Power 9 because that interface has been standardized. Okay? Other questions on this? So we also have this little thing hanging off the back of the FPGA, which becomes very interesting. This can be fiber channel, like we use in our CAPI flash solution. It could be Ethernet, so you could have a TCP/IP offload engine on that FPGA. And and it starts to enable all kinds of functionality as we move forward. So finally, just as we wrap this up, this brings program simplicity, hardware maintaining the coherency, and no device driver. A couple words on the device driver. This is the typical I/O flow with a standard Intel device driver or a standard power device driver, where you're just setting up and the acceleration is the work that you want to get done. When you look at the setup and the number of instructions running at 3 gigahertz, you end up with about 13 microseconds for data prep and put away. That's just overhead. With CAPI down here, it's about 1/3 of a microsecond. So if you had the exact same algorithm running on CAPI versus not CAPI with a standard device driver, it's going to be 40x faster. How am I doing on time? Good. So what can you start to do with this? We talked about data analytics. And if you have some software analytics running on your chip today, you're going to pull your data in, your tons of data. It's got to go through a knot hole, Ethernet, Ethernet on the backside of an I/O card, and PCIe maybe by 16 here, and you're going to get 12, 13 gigabytes per second if you're pulling in 4K blocks. And maybe you're running DB2, maybe you're running Oracle, Informix, whatever you're running here. You're pulling your data in and you're putting it in memory and starting to run your analytics on. This is a typical software model. Now, if you say, I want to do FPGA with it, now you're going to have your device driver memory, and you're going to pull from memory, send it out to the analytics, and bring it back and then put it into memory. That's what we do today with an FPGA offload. So how has CAPI helped that? Well, we got rid of the device driver. We've expanded the memory all the way out to the FPGA, so that part of it's on the FPGA. And this brings programming simplicity. It brings lower latency. Even though you're going across those electricals, getting rid of the device driver and other pieces of work there, we see a latency that's down around 850 nanoseconds total to get from the point in time that you request data, have a miss in this cache, and have to go out to main memory and bring it back, round trip 850 nanoseconds. All right, and compare that if you had a device driver, all of those data requests, instructions that added up to 13 microseconds to get things out there. You've got thousands of instructions that would need to run to get that DMA request out if you didn't have coherent memory. But the most intriguing thing that CAPI brings to this table is what we call data in motion. This is where you no longer have the data sitting off on another I/O card, but the data is actually sitting off the back of the FPGA card. You have your coherent memory and your analytics is on the fly. And I think somebody earlier, it might have been you, Steve, talked about needle in the haystack. So it's Leo, sorry. Do you get credit for a lot of Leo's thinking?
No, he definitely does not. I don't let
You
him.
make sure of it. So let's say you're looking through a Twitter database or some other kind of very large database, but you're only looking to see if your name's trending. Hashtag Nimbix, are we trending? And in the old model, you'd have to bring all of the data in to memory and then start looking through it. Here, where on the back of this card, you could have two 40 gigabit per second Ethernet connections, which is a huge pipeline of data coming in, but then only forwarding the needles that you found in the haystack through. Much more efficient way of doing things. And this is just an analytics example of that. So these are just some of the things you can do. The fact that this card here, a physical PCIe card, is an open standard makes things wide open for what you want to design. Hey, I need 8 gigabytes of DRAM memory on this card. You can buy that. Hey, I want those two 40 gig Ethernet connectors on the back of that. You can do that. right? And we have all kinds of partners who have cards out there today, and they're more than willing to design another one for you. If you need a really inexpensive card, we got that as well. So the fact that you have the open power community behind this, behind the card here, makes things much easier. So just a summary of CAPI and the differentiation. The FPGA being a peer means that you have a simple programming paradigm and much higher performance. What we just discussed, the architecture allows for any kind of FPGA, or you could even put an ASIC on there, which is what Mellanox has done for their RDMA engine. Gives you all kinds of flexibility. And virtualization is built right into the architecture. So if you were to build, say, a gzip acceleration, compression accelerator for CAPI, you could have multiple applications all calling the gzip simultaneously, even if they have different address spaces. And the PSL takes care of the context switching between each one of those applications that call in it. Leo.
So by virtualization, I assume you mean that you're virtualizing the interface. You're not plugging it into a hypervisor to then virtualize an application.
Correct.
In other words, I can use it on, you know, like on just a standard app on the kernel.
Yes.
Great.
Yeah.
Currently, it is not virtualized only. We are working to get it FPGA faster.
Okay. Well, I'm mostly interested in the container context.
Like to actual virtualization.
Okay.
So the way it gets handled today is you actually have a library function call that you would call here that gets you access out there. Right?
So I can basically slice it up on the host and then or on the kernel
Yes,
and then just
and we have open source software examples like the gzip example. You can go out to GitHub today and look at how we coded it up and did all that work.
So I had a question on your, I guess that's or the previous slide, the one that talked about the building specific types of, 8 gigs or dual 40 gigs or whatever.
Oh, okay.
Do you guys have, do you have some kind of use case map already in place, or is it still early days in that sense? In other words, are there like 5 different CAPI cards that you think cover 80% of the use cases that somebody can?
The latter. So today there are 3 developer kit companies, Nalitech, Alpha Data, and a Chinese company called Semptian. Mm-hmm. There are at least 2 more in the queue. Alpha Data is their current card is a Xilinx Vertex 7 with a KU60 coming, and then Semptian is doing a Xilinx KU. They have a KU60 and a KU115. So yeah, it just keeps going as more use cases are out there. And what's happening is open power partners are going to the card maker and saying, hey, we want to do function X. I don't know, Hadoop eraser code, right? So we're gonna offload eraser code, and Semptian is going to go make a card for it. Xilinx actually wrote the eraser code functionality, that AFU. From Xilinx, they're going to make it free for anybody. So you can go out, put it on whatever card you enable for it.
And the reason I ask is because, as you can imagine, in a public cloud provider context, you kind of want to have an inventory of common use cases versus saying, tell us what you want to do and we'll build you a card.
Yeah.
So
exactly. Yeah. So as you look at it, you want a general purpose card that can do 10 different things, not 10 cards to do each one doing one.
Well, it depends on how much optimization you want, right?
Yeah. Yeah. So we're happy to work with you, and we'll discuss what's the best fit. Some examples. So Dennis showed a region of interest as he was picking out Coke bottles. That's a analytics engine called I think you call it a little bit different, but regional convolution. What this is doing here is the top row is CAPI. So this is the raw data video feed coming in, and then this is the region of interest where it's looking through the raw data and trying to figure out what it wants to do further analysis on. And it's running at 30 frames a second because CAPI is allowing it to do that. Down here, this is the same algorithm running on a software thread that gets about 1.5 frames per second. All right, so yeah, obviously FPGA faster than software. This company is SiliconScapes. They had been doing FPGA video analysis for quite a while. When we came to them and talked to them about CAPI, they jumped on it. Within 2 months, they had created their own CAPI bridge so that all of their different engines could just plug right into CAPI. And they found that they went from about 15 frames a second to 30 frames a second once they were able to get rid of the device driver. They knew that that was a big overhead for them. So they got rid of the device driver and capitalized on a little bit better latency. Now, in this case, the video feed in the future will come off the back of the card right into the card rather than come in through system memory. So this is one example. Here's another one also from SiliconScapes. This is a motion detection. It's really small up here, but it says, hey, this is Matt, because it's actually got some facial recognition in here. But it's cycling through surprised, disgusted, sad, and happy. So what could you use this for? Well, we've got another video I didn't put in here, but it's a shopping cart where they've got a camera on the shopping cart, and they're walking along, and he picks up products, and the camera is looking at his face and understanding, hey, he's looking at Oreo cookies, and he's happy with it, or he's disgusted by it. But that's really not a compelling demo the way that if you're, let's say, gluten-free, gluten intolerant, and you're walking through, the shopping cart telling you that the product you just picked up has gluten in it, that can be really compelling, right? And now you get into all the product learning that Dennis was talking about. So there's an analytic engine that's been trained in the background that understands what all of the different products in the store look like, and then knows the ingredients, and then can go and do an analysis and say, hey, don't pick that up, or don't buy that, it's got gluten in it.
But that sounds great, but couldn't you just OCR the label and do it that way instead and just read the ingredients? I mean, I recognize the power of the technology. I'm just wondering, like, do we have this tendency to just kind of, go like for the most difficult way first instead of just doing something
you want to take it? Because
So I'll give you another example of what.
without mentioning a company name.
I'm not mentioning company names. No, I'm going to continue with this one. Is think about what online marketing gives a retailer. You go to the online market, they instantly know who you are, where you're from, basically probably figure out your age, sex, everything. They know what you looked like, how long you looked at it, did you buy it? I walk into Walmart, they get none of that. Right. But yet if I walk up to an end cap and they've got a camera there, now they can say, how long did I stay? Which boxes did I pick up? What's my demographic? And if I'm trying to target men age 30 to 50, and I have a bunch of boys age 10 to 15 looking at it, then I know I'm doing something wrong. You get that immediate feedback. So that's where this technology starts applying more immediately to retailers without having to worry about, and you can't do that with OCR, right?
So actually, that was the first thing I thought of when you said the camera on a shopping cart. I'm like, oh, you could sell that to online to marketeers, right? But then when you threw in the example of, well, let me tell you if it has gluten in it, I'm like, well, couldn't you just read the label and wouldn't that be easier, right?
Yeah, but sometimes it's hard to pick things out. Yeah.
Say, hey, you pick up this box, you go put it down. Then a coupon comes up and says, oh, wait, I'll give you 3% off of that. Now you pick it up.
That's actually in the video that we show, and it's, wait a minute.
Okay.
All right, so we're getting close here on my time being up. Another example, our IBM Zurich labs created a fast Fourier Transform. They started with it running on a Power 8 core software, then they converted it to non-CAPI FPGA, and then converted to CAPI. They've done a couple different CAPI engines, including regular expression analysis, which looks at unstructured data and looks for trends. But this FFT was pretty compelling because of what they found. This is the comparison of the three different paradigms. The light blue here is software. So a software thread was getting around 10 gigaflops per second performance, raw performance. The FPGA with no CAPI was only getting half of that. And then CAPI doubled the software. Well, why did that happen? And the answer is down here in the latency. So the software thread, of course, is accessing memory and gets it as quick as possible because it's local. But what was happening is the average latency for non-CAPI FPGA was through the roof. And this has been a barrier for adoption of FPGA for some data sets, like small FFTs weren't a good match. But then when you drop that latency way back to near what the software thread is, you see this performance double because the actual work is much faster on the FPGA. And then finally, of course, power performance is far better with CAPI versus the software thread just because FPGAs are low power consumers. So this, another example of what we've seen under CAPI. Finally, cancer treatment. There's a new type of cancer treatment called light-activated cancer therapy. And the University of Toronto, a guy named Jeff Cassidy has been studying this. What it is you inject a dye into the area where there's a cancer, and then what this dye does is if the cancer cell gets hit with light, a photon, it kills the cell because the dye has been in there. Sounds really good. You want to get that dye just into the cancer cell. That'd be great, except that when you inject it, it spreads to good cells around the area as well. So if this is human bladder cancer right here, and you've injected the dye into this whole area, this white fuzzy stuff here, that's modeling how photons will bounce around. And you have to come in and figure out your treatment such that you minimize the bounce of all the photons and have them just hitting on the cancer cells. This is a very compute-intensive algorithm. It's basically a Monte Carlo algorithm. And here's his algorithm. He's running this now on a CAPI FPGA, and the difference is incredible. When you run it in software, it takes about 2 weeks to do the modeling. Well, the problem with that is 2 weeks after you've taken the initial MRI, the cancer has grown and your results are no longer valid. With CAPI, you can get the result. He gets results in 2 hours, which means that before the person leaves the office, they know whether this is a valid treatment plan, and then they can go ahead and do that right away. So another very, very cool usage of CAPI. Without CAPI, it was running 4 to 16 times slower. So CAPI itself got him over that level into the usable time frame. This is now being going through FDA approval. So that was 3 different examples of how we're using CAPI and many of the use cases that we have out there. We have plenty more, and we're putting a catalog online soon. So, overall questions on CAPI? Up front? Yeah.
So you have a
Here, he's got.
So with that is part of the open power platform. So you work with vendors like Nimitz and things like that have that capability to use that, correct?
So we are working with Nimbix. We actually have meetings tomorrow morning to start discussing this. We started talking with you guys about a month ago about putting some of this onto the Nimbix platform.
Any comment from legal on that?
Yeah. Any other questions?
I'm thinking of possible mobile or real-time applications for this. How much of this has to be set up as a batch process? And can you imagine, say, this being used in a security setting to recognize facial recognition as people come through a checkpoint? Or, to help people who have poor facial recognition skills, remember people they've met before, that kind of thing?
Yeah. So the old technology for people coming through checkpoints is biometrics, measuring the distance between the eyes, shape of the face, things like that. The new training, like you were training a Coke can, is pictures and names. So there's two parts of the work that goes into doing what you just said. The first part is the training. All right. So another example we're working on is bank fraud detection. A particular bank has, many banks have this issue, but we're working with a particular one where somebody comes in, they open up an account. In order to do that, they need a passport or some kind of official government photograph and a utility bill, something that says what their address is. So they open up an account. They walk down the street to a different branch. They have a passport, same picture, different name, different utility bill, open up another account. And they maybe go online, open up a third one, taking a selfie. And the only common denominator is that the face is the same. So now you've got a database of 15 million faces, and you're going to go and say this one and this one are the same. No. So you can send all of that stuff through training. All of the JPEGs start getting trained. And now you have a trained database. You send in one new picture into that trained database. That's execution time. So there's training and there's execution. So now back to your border control. You've got a set of faces, maybe of people that you don't want to let into your country. It's trained on them. When somebody comes through, hopefully at the airport before they even fly in, you've recognized that face against the set of trained trained faces, and you stop them before they even get on the flight. So yes, that's the kind of thing that's being done with the neural networks that Dennis was talking about. So there's real time and then there's training. The training takes much longer than the real time execution because you can do a compare pretty quickly. But the training can take minutes per person. So it could take 2 weeks to train the database. And then, so you do a drop of the database every 2 weeks kind of thing. But the more compute power, the more systems you put in Nimbix to go work this, the faster the total time to do it for training. Okay? Yep.
Could you maybe contrast CAPI with CUDA direct memory, CUDA unified memory, I should say?
So could I contrast CAPI with CUDA and really GPU?
No,
work?
CUDA unified memory. Unified memory. CUDA unified memory.
I'm not familiar with it.
So it basically allows you to access a shared address space for the GPU and CPU memory. So it seems to me quite similar, except for GPUs rather than FPGAs, of course.
And what platform is that on?
Within the NVIDIA CUDA platform directly. So it's part of the hardware in certain device classes.
So what I'm familiar with that we're doing with NVIDIA, I think everybody's, it's public knowledge that IBM and NVIDIA have a very tight relationship, and we're coming out very soon with an NVLink, which is a much broader interface, much more bandwidth. And as we get to Power 9, you would expect us to do the full hardware-enabled CAPI coherency with NVIDIA. I'm not sure how that works. Do you know how it works?
So I have not looked at the CUDA memory model directly, but I've looked at other competing technologies. Most of them use what's called an Iommu. AMD came up with this originally. One contrast to that is in Iommu, you have to set up those pages either with a device driver, OS kernel, something has to set that up ahead of time to signify that as I/O space. So you're still doing some kind of pinning or some kind of pre-allocation of memory for that shared area. In our case, you have access. So a Power 8 system, we have systems you can put 4 terabytes of memory in. The AFU, the CAPI, can have access to that full memory as long as you've done a malloc. All you have to do is a malloc in your operating system or your application, pass the pointer to that malloc to your AFU, and he has access to the full space. So there's no overhead of device driver to manage that memory space between I/O and system. So in the CUDA case, I'm guessing they have a whole bunch of stuff overhead.
Yeah, and there's a lot of things in the driver obviously that are doing that in the CUDA case. I'm just curious because obviously some of what you describe, I'm assuming, requires modification to the hardware that's being used. Obviously, there's the part you control, the power chips and so forth, but then there's also the accelerators that are being modified in some fashion to support what you're doing.
Your accelerators are not.
So
Not being modified?
no, but we put our IP, on there, which is what he meant.
So, I see, right.
Yeah.
Okay.
Yeah.
So do you see what you're doing? I was trying to tease out what you were saying before, wondering whether you're going beyond FPGA with what you're doing with CAPI, or if you see it just being primarily for FPGA.
So that coherent protocol, the coherency is going to extend in the future to GPUs as well. And what that does is allow, now you've got an application running on a core that can send some of the data, pipeline data, into the FPGA and then tell the GPU to go work on it. And it all is in a very simple programming model where it's the same virtual address space. And you don't have to worry about pinning data or anything like that. The hardware just manages it. So just picture that pipeline moving through and sending data wherever you need it, wherever it performs best.
And is that just the shared memory model, or is there also a change in the execution model? I mean, you mentioned it sort of, you can almost treat it just like another core, but most of what you talked about was with regards to shared memory. Is there an execution model as well, or is it just for the memory?
So it's not a change of the mindset of the execution. It really just says, hey, the first thing I want to do is algorithm A, and then algorithm B, and algorithm C, and you do that today. But now, if algorithm A is best done on an FPGA and B is on a GPU, then that's where you're going to go and send it.
All right. Thank you very much. What we're going to do now is have well, first of all, round of applause